let's take a walk through a bunch of functions that are familiar to us. Now, the first of these is sine of x, and the point that I want to make right now is, let me suppose that I'm taking the limit as x goes to some specified point. How about as it gets close to this 2 value here, of this function sine of x? Well, I think for this function sine of x, it's quite clear what the limit is. So if I imagine that I'm getting closer and closer and closer to 2 from the right, and I can imagine I'm getting closer and closer to 2 from the left, what's the limit? Well, it's just whatever the height of that point is. It's just going to be sine of 2. Likewise, if I want to go down here, this is the point 3 pi over 2. If I want to figure out what the limit as x goes to 3 pi over 2 of sine of x is, well, I look here and I can see what's going on down here. I can see what's going down there. The limits from the left and the right are just whatever that point is. And so in this case, it's -1. So the point is that I can just look at this graph, and because there's sort of no holes or jumps or anything weird going on, the limit is just whatever the value of the point is. Okay, so let's see some other ones. This is another one that we saw before. This had an interesting behavior. We noticed that if I took the limit as x went to 1, well, I'd be coming along this line from the left and the right, and the limit would be equal to this value of 2, but that was not the same as the function value. The function value was this dot up here. It was this value of 3. So this is a different example from the sine, because for the sine, the limit was just always the same thing as the function value. But here, the limit is this one thing, the 2, but the function value is a different thing. It's the 3. All right, let's carry on. We've seen this example before. This has a vertical asymptote. It's got this gigantic infinite spike here. The limit from the left is going to positive infinity. The limit from the right is going to minus infinity. And the function's not even defined at 1. So it's not at all the case that the limit and the function value are the same. And then finally, I want to show you this function, the sine of 1 over x. We've seen that as well, where we're also not going to have a limit. We've got this infinite oscillation at this particular point. And indeed, sine of 1 over 0 is not even defined. So you also have this sort of kind of weirdness going on. Now note that the weirdness is only going on around 0. If I go to some other point like this, and I want to figure out what's the limit as I go to whatever that is, 1 point something, well, I just go along the curve and I just plug in the function value. If I want to know the limit as x goes to 2, say, well, it's just sine of a half, sine of 1 over 2. So for most parts, the limit's easy. You just plug in the function value, but then there's these few interesting spots where that's not the case. So the notion I'm trying to illustrate to you is something called continuity. And so we are going to say that a function is continuous if the limit and the function value are the same. Or more precisely, we're going to say it's continuous at a point A. Continuity is a local property. It's something that happens at some particular point. If the limit as we get close to it is just the same thing as the function value. So some functions are continuous for all points. Other functions are continuous for some points, but not for others. And in a few very weird examples, you have functions that are not continuous anywhere. So let's go back to one of our examples. This was the 1 over 1 minus x. If I look anywhere except for the problem spot's at 1. If I look anywhere else, then the limit is just whatever the function value is going to be. So it's continuous in all of this stuff. There's no jumps, there's no holes, there's no oscillations, there's no spikes. In this region, it's going to be continuous. And likewise, in all of this region, it's continuous. But the problem, the discontinuity, is at this point of 1. So we can say that the function 1 over 1 minus x, it's continuous everywhere except x equal to 1. And for every other point, like how about 0 or a half, it's going to be continuous. We'd previously seen this fact about rational functions, functions that are a polynomial on the top divided by a polynomial on the bottom, where we're making the additional claim that the quotient is not going to be equal to 0. And we'd previously said that for those types of things, by using limit laws, we applied our set of limit laws, we could see that this limit as x went to a of f of x was just the function value at a. In other words, what we've seen before, we can recast as saying that all rational functions are continuous, at least where their denominator is non-zero. So as long as you have your denominator be non-zero, then a rational function is continuous. So this creates a big, large set of examples of continuous functions for us. Now, it turns out that it's worthwhile giving names to different types of discontinuities. This example is one referred to as a removable discontinuity, and the idea is this. This function is almost continuous. It's just got one little problem spot. It's just this one point here was just shifted up. But let me make a tiniest change to this function. I'm going to take this point here, and I'm going to move it down. And then now we have a straight line, and a straight line is a polynomial, and it's continuous. So in other words, this original function, the piecewise defined one, with just this one small change, adding one point in from before, is now going to be turned to a continuous function. So we see that that example is a removable discontinuity because it's easy to get rid of it. However, this is not always the case. For example, in the spike, the 1 over 1 minus x, I can't put one point in and fix this. If I put in a point there, that wouldn't work because the limit from the left is plus infinity and the limit from the right is minus infinity. There's no one point I can put in here. So when we've got these infinite spikes, we'll call it originally an infinite discontinuity. Okay, let's look at a different type. This was the sine of 1 over x that we've seen a few times, and it oscillates a lot, so we're going to call it an oscillatory discontinuity. And then the final category is something called jump discontinuities. And it looks like how it sounds. We're going along for a while. Continuous in all of this region, by the way. We get to this one problem spot at 1, and then what it does is it completely jumps the function and goes off in some other path. This is not the removable discontinuity where it jumps at the one point, but then it would carry on in the straight line x plus 1 as we saw before. This is one where all the functions doing one thing and then it starts doing something completely different. And this is referred to as a jump discontinuity. So we have these removable, these infinite, these oscillatory, and these jump discontinuities as different types of discontinuities that can be.